Today's video lecture is on section 7.5, and the essential question is how do you set up and evaluate the expression to determine how much work a force does? So when we talk about work and the contributions of force, work is defined as the amount of, it quantifies the amount of effort you put into moving something. In other words, it quantifies the amount of force you apply over a given displacement. So, so we need to represent that, and we can represent it graphically. That's probably the easiest way to understand it. If we graph the push or the pull or the force on the y-axis and the displacement on the x-axis. So, for instance, a constant force of 7 newtons would mean that we have a horizontal line of at a value of 7 on the y-axis. And let's say we move something from point A to point B. Then the definition of work then is, again, that number that kind of quantifies the value of the force and how far you move something. So we define work then as the product of force and displacement, as long as the force is in the same direction of the displacement. So, so for instance, for a horizontal force and a horizontal displacement, you could find the work by just multiplying the value of the force and the value of the displacement. So from a graphical perspective then, what we're looking at is if we multiplied the force times the displacement, we'd get an answer of 70. And that's really the value of the physical area underneath the force graph. So graphically, then for a constant force, we can change this question into an area question. So the work done by a constant force is the product of the force and the displacement as long as they are in the same direction. It's also the area under the force curve. So let's just take this example here. We have a hoist. It lifts 2,800 pound car and it lifts it 4 feet off the ground. So if we draw this, we have a constant force of 2,800 pounds. We could say that we lift it from 1 foot to 5 feet. That would be lifting something 4 feet. And so the displacement then would be 4 feet, and that area would be the physical product of 2,800 times 4, which is 11,200 foot-pounds. So that would be the amount of work that force does. And it's also the area underneath that force curve. So that's for a constant force, but what happens if we have a variable force? In other words, if we have a force that changes in its magnitude. And these are 3 examples of that. Hooke's law is a law governing the force in springs as you stretch and compress them. The law of universal gravitation is what governs planets and their orbits. And Coulomb's law is what governs the electrostatic forces on charges in much the same way that universal law of gravitation explains the forces between planets and between planets and moons. Hooke's law is linear, so it's a linear relationship between force and the amount of stretch or compress you put into a spring. So if you've ever worked with a spring before, you know that the farther you stretch it, the more force you need to pull on it. So we'll look at that relationship in the next couple of slides. Linear relationship looks like this: F equals kx. These two are what we call an inverse square relationship. In other words, as the distance increases, the force decreases. So the analogy there would be like you going out into space. Then the gravitational force of the Earth is less and less on you. And so that inverse square relationship looks like something like this. Force is some sort of constant divided by the square of the distance. So the first thing we're going to look at is linear forces. So Hooke's law says, okay, we have a spring and we start to pull it, And at the beginning, we can pull it with relatively little force, but as we pull it farther and farther and it stretches farther and farther, we're going to need more and more force to stretch it. So we have this relationship that looks kind of like this. So there's your linear force. And so let's say we stretched a spring from an initial value A, like maybe this picture right here, and we stretch it, we add weight to it, in other words, we add more force to it, and we finally stretch it out to this position there. So we've stretched it from point A to point B, and it's stretched about that much, if you can see the mouse on the screen. And so if we want to figure out then the amount of work that's done, we know that the amount of work is the area under the force function. And so when we look at this shape under the force function, we see a trapezoid. So we can still, with linear forces, apply an area model to the solution of this problem. So we can look at this as area, and you can look at it as a trapezoid or a rectangle plus a triangle, however you want to look at that. But that would be one way of finding the work done by that force in that spring without using any calculus. So we also can use calculus though too, because we know that calculating the area under a function is nothing more than integration. So for instance, if we have a spring here of a set length, and then we stretch it a distance x here, we can find the work by integrating that force function from position A to position B. So in other words, from some sort of initial length to some sort of final length. So let's take a look at this Hooke's law example. Since we have a spring, it requires 5 pounds of force to stretch it 4 inches. How much work is done in stretching a 7-inch spring from a length of 12 to a length of 16? So if we think about this, first of all, we need to know the force in the spring, and we know that this force is the relationship K times X. So if we look at what we have here, we have a 5-pound force, so this is representing 5 pounds of force, and that stretches the spring to stretches it out 4 inches. And so now we also know that we want to stretch a spring from a length of 12 to a length of 16 inches. So we'll talk about that in a second. So one of the things that this initial information helps us find is that constant K. So if we have a force of 5 pounds and a stretch of 4 inches, then the K is 5 over 4. And then if we talk about A and B, remember we're stretching this spring here. We start with a spring that's 7 inches long, and it's stretched out to the point where it's become 12 inches long. And then we want to, so this basically means we stretched it out 5 inches to begin with. So really we're right here, a stretch of 5 inches. And now we want to stretch it out to a total length of 16 inches. So that means we're stretching it out then 9 more inches. So if you think about this, we've got a 7-inch spring, and it's stretched 12 inches. So it's going from a stretch of 5, and now we're going to stretch it out to 16. So it's going to go from a stretch of 5 to a stretch of 9. And so that's going to be our area then that represents the amount of work we do when we stretch that spring from a length of 12 to a length of 16 inches. And so that 5 and that 9 then become your upper and lower bounds to your integral. So once you integrate this is 5/4 times 1/2 x squared, and then we can put in the upper bounds 9 and 5 and figure out how much work is done. So after we figure that out, it's 35 foot-pounds of work to stretch that spring from a length of 12 inches, which means it's already stretched a little bit out to a length of 16 inches. Now let's look at an inverse square law example. So we have And we always say neglecting air resistance because that simplifies the problem. And the weight of the propellant. Determine the work done in propelling a 6-ton satellite to an orbit of 300 miles. And we're going to use 4,000 miles as the radius of the Earth. So when you're looking at this, this is an inverse square relationship. So as we get farther and farther apart, the force on that object, as the orbit increases, the force decreases by a square of the distance. So we need the force on this object. And the only reason we need a force on the object is so that we can determine that constant K. And so we know that when we have a satellite on the Earth's surface, its weight is gravitational weight. So if we look at the inverse square relationship, we're going to use this to set up our force on Earth times our distance from the center of the Earth to find K. So our satellite on Earth, when it's sitting here on Earth, it is a distance of 1 radius away from the center of the Earth. So that's a distance of 4,000 miles. So at 4,000 miles, if here's the relationship, the inverse square relationship, we have a gravitational weight of 6 tons. So if we put that into our inverse square relationship, 6 tons equals K over 4,000 squared. On the Earth's surface, a distance of 4,000 miles from the center of the Earth, our gravitational constant K is 96 million ton-miles squared. So that's our K, and now we're going to use that now to take this satellite from the Earth's surface up to an orbit of 300 miles. So looking at this orbit now, we know that now when it's in orbit 300 miles above the surface, then that means relative to the center of the Earth, we're out at 4,300 miles. So this is 4,300 right here, and this purple area represents the amount of work done to move the satellite from the surface of the Earth out to its orbit. So since this function is not linear, we can no longer use geometry to figure this out. We have to use calculus. So we're gonna set up this integral, and here's our force function because we found our K at the Earth's surface. And so we're going to set up our work function. It's going to be integrating our force function, and we're going to start at a distance of 4,000 miles, and we're going to take this out to a distance of 4,300 miles. So what was left to do is integrate this. So I'm going to factor out the constant of 96 million. I'm going to convert this to a negative power, and then I'm going to do the power rule. And so we end up having 96 million times negative 1 over x. So if I get that repositioned to be a little more familiar to you, and then we can put in our bounds of 4,300 and 4,000. And at this point, you can just leave the answer as such. Or if you want to grab a calculator, that ends up being 1,674.4 ton-miles. That's the amount of work required to move that satellite into orbit from the surface of the Earth. So at this point, you can do the homework for section 7.5, focusing on constant and variable forces and calculating work.